On Friday, we introduced and finished this geometric distribution explanation. So if you look at these three scenarios at the very top of the screen, you'll see something in common among all of them, and it's very similar to binomial, actually. So it is a binary situation. We're rolling a pair of die until we get doubles. We're either making or missing a three-point shot, and we could win or lose in roulette. I would say they're binary, which is confusing because this is geometric. Probability is constant every time. So each trial has no effect on the next trial, unless you argue that in basketball you're getting more tired or something like that. So we can say independent and success is constant. Probability of success is the same every time. The thing it's missing from binomial is in. It uses the word until. So this very well could be infinite. So that's the other property of geometric, that we just do this until something happens. So there is no fixed trials, and that's how it's different from binomial. So, right there it talks about how we're going to do a certain number of trials until we get a success. And on our formula chart, we have a expected value for geometric distribution, which is just 1 over p. It also has the standard deviation, but I'm not very worried about it. But just know it's on the formula chart. All right, let's actually work a problem, and we will be done with this. I don't spend a whole lot of time on geometric because it's pretty straightforward. So there's this game that this teacher plays. They're going to assign 10 problems unless the kids want to play this game of chance, and maybe their homework assignment will have fewer problems. So a student is one student is allowed to pick a day of the week, and the teacher gets a random number generator to generate a random day. So like if you number Sunday 1 and then all the way down to Saturday 7, the computer program will generate a random number. If it's a match, right away, one guess equals one homework problem. If the student is wrong and it's not a match on day of the week, then someone else is asked to guess, and you just keep going. And you do this until someone picks the same day as the computer program, and however many guesses is how many homework problems. So this could be a really good thing, could be a really bad thing, depending on how lucky they are. But on each trial, as you see at the top of the screen, probability of success is 1/7. It's geometric because you're going to do this until someone guesses correctly. So, part A, what is the probability that after playing this game, they end up having the same exact homework assignment the teacher had planned? P of x equals 10. So what this means is that a student failed 9 times in a row at guessing the day. So, they're picking one day of the week out of 7. There was a 6/7 chance of failure, and they did that 9 times. But then on the 10th guess, they got it right. And that's it. You could pick Geometric PDF to do this for you, but I think this is a lot easier to do by hand. On a problem like this, on part B, I would pull up the calculator. But we get 0357. So somewhat unlikely. This would be pretty tedious because we're talking about one guess, two guesses, all the way out to 9 guesses. So let's do geometric CDF. It asks for the probability of success. It asks for lower bound and upper bound. If you're holding the TI-84, it only asks for X, and that's the upper bound. So one more time. If you're holding the TI-84, it just says X equals, and you would type 9. That resembles the upper bound. Your lower bound is locked at 0. But the TI Nspire asks those questions, so let's take a look at it. So menu, stats, distributions, got to scroll way down. There it is. Notice we could have done PDF on part A, but CDF, so we got 1/7. 1 is 1 guess, all the way up to 9 guesses, and we get 7503. The probability that students will have fewer than 10 problems by playing Lucky Day game is 7503. All right, hopefully that made sense. Geometric is very simple. There are some practice problems assigned. Check those out. See y'all later.